This video is presented to you by Physics for Students. To know more, please visit us at physicsforstudents.com.
Welcome to my channel Physics for Students, and my name is Shaunak, and today the topic of our discussion is a very important concept of physics, which we call it as divergence. So before we start ahead in understanding what is the divergence, I would like to go back a little bit to the roots of this particular concept so that it becomes easier for you to understand. We would be dealing with divergence, a little bit of mathematics into it, keeping it as simple as possible. And at the end of this video, I have a quiz for you. Yes, a quiz which perhaps would be a kind of a brainstorming for the new generation and for the people who are into physics and mathematics. So watch the video till the end and wait for the quiz, and you can let me know the answers in the comment section of the video. First, we would start with the what is divergence? Well, divergence is basically it means to spread. But before we go ahead, I need to tell you that the importance of divergence is immense in order to understand various aspects of physics. Divergence of vector quality indicates how much the vector quality spreads out, and it is also used in convex and concave lenses analysis. Okay. So first of all, this word divergence originates from the Latin word which is called diverge. So the modern Latin diverger rather, is a combination of two words which is dis and verger. So it is formed, which means kind of a go in different direction, and it is assimilated from dis, which means apart, and verger means to tend or to turn or to bend or to move forward. So the divergence represents the volume density of the outward flux of a vector field from an infinitesimal volume around a given point. So here is a figure which actually means to spread. So it means that being apart, something which is spreading. The divergence of a vector, it measures the how much the vector function is spreading out from a particular point in space. Note that we are speaking of vector function, so I'm keeping it as general as possible so that it becomes easier for us when we come back to Gauss's law of divergence in electric field. So it becomes easier. So let me give you a very quick example that let us consider air is heated or cooled. So the velocity of the air around this red region on this picture, okay, at each point defines a vector field. So while air is heated in a region, it expands in all directions, and thus the velocity field points outwards from that region, and the divergence of the velocity field in that region would have a positive value, while the air which is cooled and thus contracting, the divergence of the velocity have a negative value. Very importantly is that if you go back to my video on history of Maxwell's equations, you will see that originally James Maxwell coined the word convergence, not divergence, and it was Oliver Heaviside, who is considered to be one of the greatest genius of all times, coined the term divergence. So it was basically convergence, which was coined by Oliver Heaviside. I really feel that Heaviside is one of the most underrated genius of our times, and he actually brought the Maxwell's equations, and he actually coincides the Maxwell's equations and coined the term divergence. So here is a figure which is quite easy, where the radial vectors are pointing out. It is a positive divergence. These which are pointing towards the center is called negative divergence, and those vector lines which are coming in and out carries a zero divergence. So moving ahead further in our video, what we are going to see is this. So once we consider what is a positive divergence, let us see a little bit more about that. So positive divergence, which is denoted by this nabla operator, which is the upside down delta, is greater than zero. So what do we mean by that? Let us draw a figure, quick figure. This is an x and y axis with a center, and we mention this point x0, y0 is positive in case you see that these vectors are all pointing outwards. So they are radially pointing outwards, and this line signifies that the divergence is positive for a particular point. Yeah, for a particular point. So at some point x0, y0, you can consider this as a vector flow, a wind flow, or an electric flow. Let us keep it just as a fluid flow for the time being. That when it comes out to be positive, the fluid flowing along the vector field becomes less dense. Why less dense? Because from that point the vectors are pointing radially outside, so obviously the vector field, whatever it is, a fluid or water, it becomes less dense. So this is how the positive divergence emerges. So consider the next part, which is the negative divergence. We will consider same when this is less than 0, and you see that the radial vectors are pointing towards the center. We take the same kind of an analogy which will be easier for you to understand, xy axis with a point, and here as you will see these arrows are pointing towards this particular point, right? So we take x0, y0 as any kind of a point, and what we get is that the divergence is less than 0. What typically happens is that when it comes out to be negative, the fluid flow along the vector field becomes more dense. Yeah. So I'm just using a physical analogy so that the things become clear. So the negative divergence means that the fluid flow becomes more dense. That means it is getting concentrated to that particular region. So we move ahead with the third part, which is the concept of zero divergence. Now, the concept of zero divergence is very important in fluid dynamics and electrodynamics. Why? Because it indicates that even though a fluid flows freely, its density stays constant, right? So this is particularly handy when modeling, what we say incompressible fluids such as water. In fact, the very idea that fluid is incompressible can be tightly communicated with this equation which we are coming. So say for example, this is again we are taking x0, y0, and these are coming out, going out, coming in, going out. So obviously at some point of x0, y0, this equation, when it comes to 0, becomes equal to 0. So the fluid flow flows freely, but the density remains constant, and this is the case of an incompressible fluid. So this is actually zero divergence. I just told you that why zero divergence is important in case of fluid dynamics and electrodynamics. Okay. So let us see that how this looks like. I mean to say, for example, if we want to see the equation of divergence, how it looks like. So it looks something like this with this hat. You understand these are unique vectors. Sometimes this nabla is also replaced with this div dot a. It is a dot product and it is something replaced, so it can be also like this. So all these three which I have shown you on the left hand side of the screen, these are all actually different representations of the concept of divergence. Okay, so now in order to understand divergence a little bit more in details, we will take help of another concept which is called a flux. Okay, so for the time being, let us understand that flux is something of a flow of energy through space. Like so, flux density. So we can consider flux density as the amount of flux entering or leaving a point, right? So remember that by convention the flux is positive when it leaves a closed surface. So let us look into this. We will take a kind of a cube, okay, because I want to make you show that how it varies. So we will take that cube and we want to measure with the sides length. So for example, if you want to calculate the net flux, so what we will do is that we will take the x components of this particular cube and which changes in the x direction. So we mention it is as dx. Then we take the y components which changes in the y direction. We take it as dy. Then we take the z components which changes in the z direction, and we take the dz, right? So to get the next net flux, we see that how much the x components of flux changes in the x direction. Add to that the y components of the flux. Okay, so here is a definition. It represents the volume density of the outward flux of a vector field from an infinitesimal volume around a given point. So this is just a presentation, right? This is a kind of innovation that what actually flux would represent. So we want to measure. So to get the net flux, what we do is that we add up the component x component from the x direction added with the change in the y component in the y direction and the z component in the z direction. For example, if I show on the left hand side bottom of your screen 1 minus 3 plus 4. So what I'm trying to show you is that, for example, if there is a change in the x direction 1 unit and a movement in the negative direction of y in 3 unit and a movement of positive 4 steps in the z direction, so we get 1 minus 3 plus 4, which actually indicates the movement of the vector flows in x, y and z direction. So in case that these are 0, I mean to say all the x, y, z are not moving, they have a 0 divergence. So this is what I try to show you. So the total flux change would be the field change in the x direction plus the field change in y direction plus the field change in z direction. Taking forward with this total flux change, what I would like to tell you is now you will understand why we are using partial derivatives. So obviously the question comes that why in those equations we have partial derivatives. So let us move ahead with that. So what we are doing is that we are calculating the total flux change in the x, y and z direction. So we take and on the left hand side, let this cube be there where it is. So in a pseudo mathematics, we can say that divergence is a limit where the volume is tending towards zero, flux divided by volume. Okay, and this can be represented in this kind of a I would say this kind of a equation. So now let us see that these are actually the gradient which gives us the partial derivatives, and these, so this is the dot product with our vectors which gives us the divergence formula, and these are actually the partial derivatives, right? So now it comes clear to you that why we are using the partial derivatives, and div is represented by this nabla with a dot operator. So I hope now it becomes clear, because we are taking the change in the x direction, y direction, z direction, maybe with further higher dimensions which might follow. You can take the divergence of the 4th dimension or 5 dimension. So understand this concept is quite clear that once okay, let me again go back to the previous slide so that it becomes clear to you. Yes, so the total flux change when we are trying to point out in both x, y and z direction, so definitely we have to take something like this, which is the dot product with the vector, and these are the partial derivatives, and that is why we are taking the partial derivatives. Why? Because we are dealing with more than one variable. So the now I hope you understand that why I talked about flux, because the inflow and the outflow around the region of the cube actually is determined by flux, which in return is determined by divergence. In the video, in the coming few minutes, you will see that there is quite a good and an intimate relation between divergence and flux. Okay, so we got it that divergence equals to flux by volume and divergence is flux density. These are pseudo mathematical terms. Let us not go that these are exactly terms, but this is just to give you a kind of a feeling. So moving ahead with that similar cube, I got this equation. So this is why it is called the change in the x direction, where the x remains constant, the change in the y direction, the y remain constant, and change in the z direction, where the z's remain constant. So this is the reason this equation forms out of the 3 variable changes x, y and z. Okay, and how do we do that? By keeping the denominator constant, a typical form of divergence, partial derivative. Few points I would like to note: that divergence is a single number like density. Divergence and flux are closely related. So if a volume encloses a positive divergence, it will have positive flux. Divergent means to move away, which may help you to remember that divergence is the rate of flux expansion, positive divergence, or contraction, negative divergence. Okay, so far so good. So now what we will do is that let us give it a formal definition of the divergence, obviously 2 direction. Now the mathematical definition of divergence may be understood by considering the flux through an infinitesimal surface surrounding the point of interest. So if we are to form the ratio of the flux of a vector field, okay, so let us look into this. This is exactly what it looks like, right? So if we are to form the ratio of the flux of a vector field A through a surface S, now consider this A is just a vector field. I have not yet defined whether it is electric, magnet. Let us keep it general vector field through a surface S to the volume enclosed by that surface. As the volume shrink towards 0, you have a divergence of this. So let me divide this further equation. This one can be defined as this, with 2 dimensions, 2 variable. This one can be defined as this, right? So f of xy is a 2-dimensional vector field. Xy, let us be, it's a specific point on a plane. And this one actually denotes what is called the flux integral. So we'll come to that, don't worry. So these are the different components where we are formally defining divergence using the concept of limit. Right. So, and dA, let us consider that this is a mass leaving each tiny pieces of any element which has got of a size of dA. Right. And this could have written it as f, the volume integral with a surface S of f, but I have just kept it A because I really want to show you how this A gets replaced into the electric field. So f is basically the flux. So I just wanted to show you that this could have been written in this way. Either way we can go ahead. So these is the formal definition of divergence in 2 dimension, and I have explained those parts. So let us go ahead with this and we will define further. This is the what we call it is a 2-dimensional vector field, right? And this is how it is. It could have been written. So xy is a specific point in a plane. Okay, vxy is some region in the xy plane. This is the volume. And this is something you can call as axy, so vxy, something which shrinks around the point. S is a surface integral, and limit is something which I just gave here as, let us consider that vxy is tending and going towards 0, and n is the unit vector, and this one is the flux integral. So in order to divide further, I just showed you that these are the different ways in which you could have you could have considered those areas. So this is something which is the formal definition of divergence in 2 dimension along with the elements. This one which I just circled around, this is the flux per unit area, and this part, the inner one, is the flux through the surface, which we have denoted as S. Okay. Now this formal definition, which I can further say it in 3 dimension, I've just taken this. So everything remains the same. So instead of xy, we put another variable xyz. So this is some region in place. The volume increases to another variable, surface integral, flux integral, limit goes to the same, only the z once adds on, and it goes on as the unit vector. So this is the formal definition of divergence in 2 dimension and 3 dimension along with the different components, so that when you see the 2 dimension as well as the 3 dimension, things are quite clear for you. Okay, so go ahead with this, and we can also write in this way. I've just written in these 2 formats so that once you see this and see this, you don't get confused. So we can tell that divergence, so this is the definition, the divergence of a vector field at a point is defined as the limit of the ratio of the, so limiting ratio, right, of the surface integral out of the surface of a closed volume V as V shrink towards 0, which I have shown just a few seconds earlier, that how we are defining that delta V in terms of xy for 2 dimension and xyz for 3 dimension. So that stands out to be a kind of a understanding. Right. Okay, so what next? We come across what we know is called flux and divergence. Now, these 2 things are quite closely related to each other, and I really want to show you the relationship between flux and divergence. So I won't call it as a difference, but it would be a kind of a relationship because it helps us to understand divergence in a much more better fashion, right? Okay, so first of all, we see what is divergence is amount of flux entering or leaving a point, and this is the electric field lines passing through a uniform surface area. So divergence, first we get it is related to point, this is surface area. So net, it is also net flux per unit volume. This is the called flux density, and it is the amount of something. This is because just to make you on a very generic way, something passing through a surface. Next, what we get that it deals with the flow of vector field. It also deals with the flow of vector field. So these are two more or less similar. So this is defined over individual points. This is defined over an area, which is quite obvious. So this is all in all what we call the relationship between divergence and flux. So it is important because it helps us to understand things well. Okay. Now the relation between flux and divergence is better explained, which is called Gauss's divergence theorem. Now This is the 3D version of Gauss's divergence theorem. It relates the flux of a vector field through the closed surface to the divergence of the field in the volume enclosed. Okay, so the Gauss's divergence theorem, what does it states? That the vector's outward flow through a closed surface is equal to the volume integral of the divergence over the area within the surface. Let us see it one by one. This we know it is as a closed surface. This we know is a surface integral. Okay, this is a vector field which you're taking as A to be very generic. This is obviously the volume integral. This is divergence, which is the nabla operator. This is a vector field. This is volume, and this is the definition. So you can just take a pause and read it out, but I will just tell you the most important feature, that the Gauss's divergence theorem, now it states that the vector's outward flux, the things which is going out, you know, just imagine, close your eyes and imagine the radial vectors which are pointing out through a closed surface is equal to the volume integral of the divergence over the area within the surface. So it is taking the integral or the sum up of the volume. So the sum up of all sources subtracted by the sum of every sink will result in the net flow of an area. So the Gauss's divergence theorem is the result that describes the flow of a vector field by a surface to the behavior of the vector field within it. So I can tell the divergence measures the outward flow of a fluid, for example, at individual points, while the flux, again, the divergence measures the outward flow of a fluid at a point, while the flux measures outward fluid flow from an entire region. We will go ahead and we will understand things on a better way. So this is just to give you the divergence theorem of Gauss so that it can understand between flux and divergence theorem. So let us see what are the components of the divergence theorem. So this is the left hand side, this is the right hand side. So this entire part I will call as the flux, which measures the outward flow of the region. I just told you that the Gauss's divergence theorems first states that the vector's outward flow, so this measures the outward flow. And this part is actually the divergence which measures the outward flow at individual points. So this is the outward from the entire region and this is for the individual points. This one is the vector field. Because it is 3-dimension, for easier understanding I made it x, y and z. This is obviously the surface. This is the closed surface. This part, which I have just make a kind of a hemisphere red, is the divergence. And this is the tiny bits of volume V which you're actually adding on. So it adding up the bits of divergence gives the same result as the flux. And this is the 3-dimensional volume. So I hope now the things become clear, the components of the divergence theorem, why I am showing it and why this is something which is important, integral part in understanding our concept of divergence, the Gauss's law of the divergence theorem. Few of the important points which I would like to tell you before we move ahead. So first of all, the divergence measures the outward flow of a fluid and the flux measures the outward flow from an entire region. Second, the divergence theorem is a tool for translating between surface integrals and triple integrals. Remember that sometimes integrals become so messy, so huge that it is very important that we know the divergence theorem. It makes things much more easier for us. Now, the divergence theorem also says that when you add up the little small tips and bits of the outward flow in a volume using a triple integral of divergence for the 3-dimensional part, it gives the total outward flow from that volume as measured by the flux. It relates the flux of a vector field to the divergence of the field in the volume. And lastly, the surface integral of a vector field over a closed surface, which is the flux, is equal to the volume. So the surface integral is equal to the volume integral of the divergence over the region inside the surface. Right. So things become very clear. So now, unlike Stokes' theorem, you can say that yes, divergence theorem only applies to closed surface, but it doesn't matter. This is basically what are the important points, how the divergence theorem and the flux are related to each other. Okay. So we take this one further. And this one, which we call, I have reduced it, okay, to a single integral sign just to make things easier. And F will remind you that we are talking of the flux. So this is the surface integral and this one is the volume integral. And this is again a kind of the surface integral, which is on the left hand side of a vector field over a closed surface, which is called the flux through the surface, is equal to the volume integral of the divergence over that region entirely inside the surface. So taking ahead with the reduced version, this is something. So you might be wondering why I am explaining things repeatedly. This is important so that you understand the two relation between divergence and flux. Okay, so far so good. Now this part actually also tells that the flux is a flow of something through a surface. I am taking this reduced version with a single integral. Flux depends on density, obviously. It speaks about the total surface area, the components of flux density, which is perpendicular. Only the perpendicular part, remember, is obtained by using the dot product, and the next flux is given by the integration of F dot n over the entire surface S. So these are the important points of what are the things related to flux. Divergence is also definitely a flux, but it is the flux through an infinite similarly small volume. So that is why we have taken parts of that, and divergence is the volume density of a flux. Yeah, it is important. So these are the points which will make you understand about the relationship between flux and divergence. Okay. So moving ahead further with our video, what we come across is that now you see first of all, what I would like to tell you here is that this expression which you are currently seeing right on the top, okay, is the entire left hand side of the differential form of Gauss's law, right? You have seen that, and it represents the divergence of the electric field. Now in electrostatics, all electric fields begins on point of positive charge and it terminates on the negative charge. So it is understandable that this expression is proportional to the electric charge density at the location under consideration. Now if you see, so the Gauss's law of the differential form is on the left hand side. I have just taken the divergence of the electric field right there. Okay, now if you see, these are the electric field equations of simple object. This is for the point charge, this is for a conducting sphere, and this is for the uniformly charged, a kind of an insulated sphere. Okay, now what I'm going to do is that I'm going to show you the divergence equations mathematically with the usage of a very simple example. Okay, so I am just taking this one, the left hand side, this red one, because this is the point chart. So we are going to consider this. Okay, so we take and we see that there is a 1 upon r square factor. So hold on, I just wanted to tell you why this is. So the spreading out of the electric field is exactly compensated by this 1 upon r square reduction in field amplitude, and the divergence of the electric field is 0 at all points. Okay, so let me explain you what I'm trying to tell you. So we will take this one, the formal definition of divergence, and we are going to also take this one. Now you see what I have done is that I have used this general vector field, which was A, which I started with the lecture right at the beginning, is now being replaced with the electric field E, which is the convention of electric field, right? So we are considering this term, first of all, number one. Then what we do is that we consider this surface a Gaussian surface surrounding a point charge, and you can understand from the figure that this is a sphere. Okay, so what we do is that we take this divergence equation, and what we do is that we substitute this E with this one. Okay, so as you see right on the top left side, I have taken this one, Gaussian surface around the point charge. So I have replaced this one. So simple. So along going with the equation, we get this. So what we do now in this surface integral, we have put 4 pi r square. Why? Obviously because this is the surface area of a sphere. These two gets cancelled out. This comes in. Okay. And then this comes in. But this is actually the average charge density. Okay. So as this delta V is just the average charge density over the volume delta V, but as delta V shrinks to 0, so you see it is limiting approaching 0, this becomes equal to Q, the charge density of the original part, and thus we get the origin of divergence, which is this. Okay, so again to tell you, because this delta V is the average charge density over the volume delta V, and as delta V shrinks to 0, okay, so this becomes equal to Q, and that is the charge, which is the charge density at the origin. So I have now, you see that we have got the differential form of Gauss's law. Left hand side charges speak of the divergence operator, and on the right hand side you see this. So this is exactly a simple way of using Gaussian surface and using the 4 pi r square part into this, and we get the total value. Okay, so we got this one. Now you see we get this one, which we have started. This is divergence of the electric field, and this one is the electric charge density, which is the electric charge density divided by the permittivity of free space. So you can understand this is what we actually arrived into. Now, we also have divergence in non-Cartesian coordinates, which is a spherical coordinate. We can also get a cylindrical coordinate, and what we are talking about, the quiz part, is this. Now I have been going through many research papers. I myself tried to deduce, but still there is a question which I would like to ask the viewers, is this: is divergence coordinate free? Now the divergence of a vector field we know is defined as the limiting ratio, but the divergence is it a true vector field operation which results in a kind of an independent coordinate free divergence? Is it so? I mean to say, this is my question. This is a quiz which I would like to know, and I really don't have the answer. So if you really do have an answer, is divergence coordinate free or not, let me know in the comment box. I would really like to know, and I would really like to exchange ideas with you. So just give it a thought when you have time. Okay, so coming to the final part of our video, I would like to show you something very important. Now, let us consider this figure. Okay, where you can see there is a point. Let us consider charge or anything, and these are the radial vectors which are pointing out. So the flow lines you can see are clearly representing something which we call as a positive divergence. So you see that in here and in here and in here, all these areas which I'm marking in red, these are linear increment. So if you closely look at the picture, right from the center, as the vectors are pointing out, these are linear increment. They are increasing. Definitely they are increasing, but they are linearly increasing. So we get a kind of a positive divergence. Now we get a kind of a figure like this. Okay. Now you see this part is obviously a positive divergence, obviously, because they are radially moving out. But have you noticed another part? These parts, right, they are also getting shorter and shorter at greater distance from the center. So the question is that, does the spreading out compensate for the slowing down of the flow? So the amplitude of the vector field decreases as a square of the distance from the origin. So the radial vector tells that decrease in amplitude is because, you see, these are the arrows. Let me show you again. This is basically the decrease in amplitude. So the length gets shorter and shorter from the distance. So the decrease in amplitude is because of the 1 by r square actually have zero divergence everywhere except at the source. Why? Because it is decreasing, and these factors are getting cancelled off, so we get a zero divergence. This is a very, very important point. So note that amplitude of the vector length is decreasing as a square of the distance from the origin. Okay, so taking ahead with that, what I wanted to show you is that the key factor in determining the divergence at any point is not simply the spacing of the field line at that point, but whether the flux out of an infinitesimally small volume around the point is greater than this one, greater than flux out is greater than, equal to, or less than the flux into that volume. So this is very, very important. So if the radial vector fields decreases in amplitude, so here is a figure. If the outward flow, here comes the outward flow, this green one, the outward flow is something which is this one. Outward flow is greater than, so the outer flow are the black one and the inward flow is the green one. If it is greater, the outward flow is greater than, it is negative. Then sorry, it is a positive divergence, right? If the outward flow exceeds the inward flux, the divergence is positive. But here you will see this one, thus this comes the green line. So you see that outward flux, that those black points which are pointing outwards are less than the inward flux, so the divergence is negative. And obviously, so this comes as negative. And if the outward and inward fluxes are cancelling each other out, then it is obviously zero divergence. So in the case of a point charge, remember that at the origin the flux through an infinitesimally small charge is non-zero only if that surface contains the point charge. So everywhere else the flux into and out of the tiny surface must be the same, and the divergence of the electric field must be zero. So let us find out what we have learned in this. We have learned what is a divergence. We have learned what are the different types of divergence. We have learned what is the definition of divergence. I'm sorry, these are overlapping. What is the flux of a divergence? What is the divergence theorem? Divergence in non-Cartesian coordinates, and divergence of the electric field. So considering all those things, this is what concludes our discussion on divergence. I think that it is nice, and I have tried to give non-mathematical, mathematical, with pictures and others concept of divergence. So the next topic of our discussion is Gauss's law for magnetic fields. I will wait for that quiz, and I will wait for your comments that whether divergence is coordinate free. Do let me know in the comment box, and do like, comment and share this channel, and do let me know how do you like the video. So keep well, stay happy, and stay alive, and stay absolutely fresh like a green grass, and we will soon meet you in the next video. Bye and take care. This is Shaunak signing off from Physics for Students.